Section C, Domain and Range. In today's video, we're going to learn how to identify the domain and range of relations. So a domain of relation is a set of all the x values in the relation, whereas the range is a set of all the y values. To help us identify the domain and range of a relation, we're going to use something called interval notation. So let's look at our first example. Here we have a graph, and we're going to identify the domain and range of this graph. So think about taking each individual value and just figure out where it falls on the x-axis, because the x has to deal with the domain. So I notice that each of my x values, and this arrow means it continues on and on forever. So I know my very first x value is at -1, and then it goes forever in the positive direction. Let me clean up the picture a little bit. So that means, again, we had our smallest x value was -1, and then it continued on forever in the positive direction. So now we need to translate that domain into interval notation. So I would say the domain, which is our x variable, such that x is, now we start with our smallest value, so x is greater than or equal to -1. And that's how you write interval notation for a domain. Okay, I'll do the same thing for the range. So I'm going to imagine graphing each of these y values onto my y-axis so I can figure out where I start and how far I go up. So here my range begins at -3 and then continues up forever. So I would say that my range value, therefore, must be from -3 up to infinity. So let's see how we can do that in interval notation. So I'd write range is the y such that y is greater than or equal to -3. And that's how you define your domain and range of relations using interval notation. Remember, the straight line is read such that. Okay, let's look at our second example. I want to figure out my domain, so I want to imagine graphing each of these points onto my x-axis so I can figure out what x values apply. So let's see, let's kind of start here in the middle. So this graphs onto the x-axis and it keeps going in the positive direction forever. And then on this other end, the left behavior keeps going down and out. So that means I have all the negative x values. So I have all the real numbers. So how we write that is we say x such that x is an element of the real numbers. That means I include all real numbers. Okay, let's look at our y values. So it starts, our highest y value is at 1, and then it goes down because my graph is concave down, it keeps going down. So I'd say my range is y such that y is less than or equal to 1. Okay, here's a rational function. So we're going to say our domain, we go on forever and ever, and then we have this asymptote which has no values. It never actually reaches the x value of 2, and then we keep going on forever in the positive x values. So we're looking at this, the only problem is the x value of 2. So when I'm writing my domain, I would say my domain is x such that x is not 2. So x cannot equal 2. And now let's look at our range values. So we start forever ever in the negative direction. We go up till we hit this asymptote, this horizontal asymptote at y equals 1. We don't have any values at y equals 1, but then we go back up. So again, it's all the real numbers except for that y equals 1. So I'd say my range is y such that y is not equal to 1. Okay, example A, let's look and see if we can identify our domain. So our smallest x value is here at 8, largest x value is here at 8, but then that arrow means it continues on and on forever in the negative direction. So we would say our domain is x such that x is less than or equal to 8. Okay, now looking at our y values, our smallest y value appears to be about -2, and then it goes up from there. So I'd say my range is y such that y is greater than or equal to -2. And example B, here notice that we have all the real numbers on the domain, all the x values on the domain. So I'd say my domain is x such that x is an element of the real numbers. And then looking at range, my minimum value, it has a y value of -1, and then my graph goes up from there. So I'd say I have a range y such that y is greater than or equal to -1. Oh, forgot my equal to sign. Y is greater than or equal to -1. Okay, what if we don't have the graph? What if we have the equation instead? Well, we do the same thing, but just kind of think about what's happening in our function. So looking at A, we have the square root of x minus 5. So we know that we cannot have a negative underneath a square root, or it gives us an imaginary. And we're only looking in the real number system. So I have to say that x minus 5 must be greater than or equal to 0. So solving that little equation, I get x must be greater than or equal to 5. So that means that's my domain. Domain is x such that x is greater than or equal to 5. Now, range is a little bit harder, so we got to think about what's happening to our graph here. So if I plug in 5 into my equation, which is the beginning of my x values, where my x's start. So I plug 5 into this equation, so I figure out what f of 5 is equal to. I get 5 minus 5, which is 0. So that means when my x is 5, my y is 0. So it starts at a value of 0. Now I know that if I keep increasing this x values, regardless of what it is, when I take a square root of a positive number, I'm going to get a positive answer. So I know my range is always going to be greater than that 0. So I'm going to say y such that y is greater than or equal to 0. Now you can also look at this graphically. You could figure out what the graph of the square root of x minus 5 is, which we'll start with that point we figured out. We figured out we have the point 5 comma 0. Then plugging 6 into my equation, I get 6 minus 5, which is 1. Square root of 1 is 1. So I have another dot. And then plugging in 9. We end up with 2. So we end up, the graph looks like this. So it's easy to see graphically that our domain is x such that x is greater than or equal to 5, and our range is all y values greater than or equal to 0. Okay, what if we're asked to figure out the domain and range of a rational function? So let's look at part B. Here is f of x is equal to 1 divided by x minus 5. Now the key here is this is a rational function, and we know we cannot ever divide by 0. So let's say that x minus 5 therefore cannot equal 0. So that means x cannot equal 5. So our domain is everything except 5. So domain is x such that x is not equal to 5. Now, to think about what the range would be when I'm putting in values other than 5. So if I plug in like 6 or 9 or 10 or different values in here, Notice what happens to f of x, what happens to our y value of our function. So let's say, let me let x equal 10. That gives me 1 over 5. X equals 1,000. That gives me 1 over 995. So notice that these numbers keep getting closer and closer to 0, but we never ever actually reach 0 because we have 1 divided by something. So when you have 1 divided by something, you can just keep breaking it into pieces, but you can never ever equal 0. So I know that my y will never be 0. But if I put in a very big negative number, I would get some negative numbers. So I can get all the values in the universe except 0. So my range would be y such that y is not equal to 0. All right, let's look at our last example. F of x, 1 divided by the square root of x minus 5. So again, because of square root, I know that that x minus 5 must be positive, and because it's division by that, I know I can't equal 0. So I'm going to say x minus 5 needs to be greater than 0, or x is greater than 5. So my domain would be x such that x is greater than 5. To find my range, I'll think about when I plug in values greater than 5, what's happening to my x? Well, I'm getting positive numbers because I'm taking a square root of a positive square root, which is always going to give me positive. And I'm also, since I'm greater than 5, remember I can't ever reach 0. So again, I have this fraction, a constant over a variable. And so I will always be a positive, and it cannot ever be 0. So I'd say that in my range value. So range is y such that y is greater than or equal to 0. And that's how you find the domain and range of an equation.